During the last lecture, I introduced the definition of vector bundle and sections. Today I will use these notions for giving the definition of local and global frame and vector fields. So suppose that E is the total space of a vector bundle. Then a local frame for E is an ordered K tuple sigma 1, sigma 2, sigma k of local sections over an open set U contained in M. M is the base of the vector bundle, whose value at each P in U is a basis for the fiber EP. If U is equal to M, then instead of using the adjective local, use adjective global. If tau is a section of E, this section can be local or global. And sigma 1, sigma 2, sigma k is a local frame over this open set here. Then at each P in U, you can write tau evaluated at P equal tau I at P multiplied by sigma I evaluated at P. Here I am using the Einstein convention, where tau I are functions known as component functions of tau with respect to the given frame. We will use all this definition here with E equal Tm. The tangent bundle I introduced last time. Now let's talk briefly about vector fields. A section of Tm is what we call vector field on M. Concretely, this is a smooth map defined on an open set of M. If the section is local, this is a proper subset. If the section is global, the open subset coincides with M. And this smooth map associates to each point a vector that is an element, tangent vector that is an element of TPM. If U phi is a smooth coordinate chart, smooth coordinate chart, and the components of phi are x1, x2, xn, then for each index I varying between 1 and n, we have a smooth spatial vector field known as coordinate vector field on U denoted by ddxi, whose values at p is ddxi at p. This is an object, a tangent vector we defined before. Now let's talk about the action of functions on vector fields. So suppose that M and N are smooth manifolds with or without boundary, and suppose that this is a smooth map. We denote by df the map defined on Tm with values in Tn. The map defined such that its restriction to TPM is the map df p which is fine on TPM, of course, and takes value in TF of B n. Since DFP sends tangent vector in TPM to tangent vector in TFPN, the map DF sends vector fields on M to vector fields on N. The set of all vector fields on a manifold is denoted by this symbol. So this is a set of vector fields on N. Now it's time to introduce the operator, the map known as Lie bracket. If X and Y are vector fields, then you can define the Lie bracket of X and Y as a map from C infinity M to itself, writing what follows. If F is an element of C infinity M, then X, Y of F, this is X of YF minus Y of XF. It's possible to prove that XY is a vector field. So this defines an element of K of M. Precisely, it's possible to prove that it's a derivation. Now, the next important goal is to introduce the notion of metric on a smooth manifold. The object of this course are Riemannian manifolds, that is a smooth manifold equipped with a metric. The complete name of a metric is a metric tensor. So now it's time to review the notion of tensor. Let's suppose that V is an n-dimensional vector space And in what follows when necessary, I will use a basis of V which is always supposed to be ordered. I want to recall that V star is the notation for the dual of V, and if let's say also that this is the space of linear functionals on V, also known as covectors. The reason why we talk about covectors is that covectors are the simplest example of tensors. Precisely, they are tensors of rank 1. The rank of a tensor is the number of arguments. So covector are tensors having just one argument. I want to recall that if Bi is a basis of V, then we can define beta I in V star, writing beta I of Bk equal delta Ik. So this is equal to 1 if the indices take the same value, and it is equal to 0 if the indices are different. Beta I form a basis of V star, and this is known as dual basis to Pi. If omega is a covector, then you can write omega as follows. You can write this as omega j beta j. Also here we are using the Einstein convention. Where omega j is given by omega evaluated at Bj. There is also a formula for the action of omega on an element of V. So remember that omega is a linear functional on V. So if you let omega act on V with V equal Vi Bi, then you get omega j Vj. This is a simple computation you can do. It follows from the linearity of omega and this expression. So that's all you need to know about tensors of rank 1. Now, what about higher rank tensors? They start from the covariant K tensor on the vector space V. This is a multilinear map F defined on V times itself K times its values in R. Instead, a contravariant K tensor on V is a multilinear map F, which this time is defined on the product of K copies of V star. Let's introduce the notation for the spaces of tensor we will use. So we have TKV. This is a notation for covariant K tensor. TK V star. This is what we call, this is a symbol for the contravariant K tensors. And we have also mixed tensors of type KL. This is a multilinear map as usual. F which is defined on a product of spaces where V star appears K times and V appears L times. This notation here TKL V is used for the set of mixed KL tensors. I already told you what is rank of a tensor. Rank equal number of arguments, and by convention a zero tensor is just a real number. Tensor can be multiplied. We have two products, two kinds of product. The first one is the tensor product. If F is an element of this space and G is an element of T, P, Q, V, we can define F tensor product G is an element of K plus P L plus Q V by the following formula: F tensor G evaluated at omega 1 omega K plus P V1 VL plus Q as sorry, I have to write the indices as lower indices because these are vectors, as F evaluated at omega 1 omega K V1 VL multiplied by the number G omega K plus 1 omega K plus P. Now there is a risk that you cannot read. V L plus 1 V L plus Q. The tensor product is useful for writing down a basis of T, K, L, V. This is given by all the tensors of the form BI1 tensor, BI2 tensor, tensor BIK, tensor beta J1, tensor beta JL. Where I'm using the fact that B, let's write I, this is a basis for V, and beta J, this is a basis of V star. Of course, sorry, I omitted something. Of course, these indices I, P varies in the range 1n. The same is true for JQ. But it's important, of course, that you have only k factors of the form BIP and L factors of the form beta JQ, because you want a tensor of type KL. By the definition of this basis, it is clear that BI1 tensor BIK tensor beta J1 tensor BJL act on beta S1 beta SK BR1 BRL as follows. This is delta I1 S1 delta IK SK delta R1 J1 delta RL JL. Since this is a basis, then if you have an element of TKLV, you can write it as a sum of F J1 JL I1 IK BI1 tensor BIK tensor beta J1 tensor beta JL. Where this is a number, this is F evaluated at beta I1 beta IK BJ1 BJL. It's useful maybe to know that there exists some identifications between some spaces of some tensor spaces. Precisely, we have that T0 V, this is R. I told you before that a zero tensor is just a real number. For the same reasons, you have that T0 V star is R and T00 V equal to R. We have also that T K0V is a TKV, T0KV is TK V star, and when K is equal to 1, you get that T1V is V and T1V star is V star. It is also possible to prove that T11V can be identified with the space of endomorphism of V. Before presenting the second kind of tensor product, I want to introduce the notion of trace or contraction. This is an operation which lowers the rank of a tensor by 2. Let's start giving the definition for 1-1 tensors. In this case, we will get a zero tensor if we apply the trace operation. Because this is a 0, any element of R can be seen as a 0, tensor. So trace this is defined as just writing trace of F equal trace of F regarded as endomorphism. So now I'm using this fact. So essentially, how to compute the trace of a 1-1 tensor? You write down the matrix associated to F, and you take the elements on the diagonal, and you consider their sum. What about the trace of a k plus 1 L plus 1 tensor? This is a KL tensor. Define this way. This is a tensor which needs k plus L arguments. So I will write omega 1, omega 2, omega k, v1, vl. And this is defined as trace of the 1-1 tensor given by f omega 1 omega k dot v1 vl dot. This makes sense because omega 1, omega k, v1, vl are fixed and only these two arguments are free to vary. It's possible to write down a formula. Trace of f is a tensor whose components are related to the components of f by this formula: I1, Ik, M, J1, JL, M. So this means that you equate the last index on the top, on the bottom, and you make the sum. Of course, this formula works also for 1-1 tensor. Covariant tensor f in tk v star is symmetric if f of v1, vi, vj, vk is exactly equal to f of v1, vj, vi, vk. In other terms, if you change the position of the arguments, you get the same number. For every 1 smaller or equal than I, smaller than j, smaller or equal than k. The tensor product we introduced before of symmetric tensor is not a symmetric tensor. try to prove this as an exercise. In order to fix this problem, we define an operation called symmetrization of a tensor. Precisely, we will consider this case F covariant K tensor. Then the symmetrization of F is the symmetric tensor defined by this formula: 1 over K factorial sum on the permutation sigma in Sk of F V sigma 1 V sigma K, where Sk is the group of permutations of K elements. And now we are ready to define the symmetric tensor product, because we have all the ingredients. Symmetric product if F are symmetric, if F is a symmetric K tensor, covariant, and G is a symmetric covariant L tensor, then we can define the symmetric product Fg. This is a symmetric covariant K plus L tensor, just writing Fg equal symmetrization of F tensor G. Special case which is useful for us: K equal L equal 1. So this means that we are working with covectors. If omega and eta are covectors, then the symmetric product of omega and eta is 1/2 omega tensor eta plus eta tensor omega. if omega is equal to eta, then I have that omega that will be written as omega squared. From this formula, it is equal to omega tensor omega. So there is no difference between the tensor product of a tensor with itself and the symmetric product. I think I gave the definition of Tp star m. This is a dual of Tpm. It is known as cotangent space. Using this joint union, you can create a new bundle, vector bundle, known as cotangent bundle. And you know that elements of Tp star m are covectors. Now we want to do more, and we want to work with tensors on ppm of higher rank and introduce the corresponding bundle. So we can define the bundle of KL tensors It is noted by this symbol, and this is the disjoint union of TKL TPM. I need this definition because I want to introduce the notion of tensor field on M. This is defined as a section of T, K, L, Tm over M. Special case, a section of T 01 Tm, that is K is 0 and L is equal to 1. This is what we call covector field. And it's possible to prove that T0K Tm, this is the same as T K Tm and using this notation we can introduce the symbol we will use for the set of smooth covariant K tensor fields on M. This is tau K M, and this is defined as the set of sections of Tk T star M. So this symbol here means sections. Now I want to introduce the coordinate expression of KL tensor field In order to do this, I have to suppose that EI is a smooth local frame on Tm. I gave definition of a local frame at the beginning of this lecture over the open set U containing M. We can associate with it a dual coframe. It is denoted by epsilon I and what is the definition of epsilon I? Epsilon I of Ej, this is delta Ij. So, example, If you have ddxi as a local frame on Tm, the dual coframe is dxi where xi denotes the ith coordinate function. So you can write this once you choose a chart. So if f is a KL tensor, then its coordinate expression is this: f equal fj1jl I1 ik di1 tensor dik tensor dxj1 tensor dxjl, where now this is not a number but it's a function, smooth function the last thing I want to say about tensors is to review the notion of pullback. Of a tensor field. In order to do this, I need a map between two smooth manifolds. And let's suppose that A is a covariant tensor field on N. We can use the map F for defining a tensor field on M. So we can define for each P in M df P star A in Tk T P star M. This is what we call the pointwise pullback of A by F at P. and we write that df star PA of V1 PK, this is equal to, what is the natural definition we can give? We have a tensor on a tensor field on N. So the idea is that you send these vector, these tangent vectors, two tangent vectors on N, and then you let A act on them. So we just write df PV1 df PVK, and we let A act on these k tuples of vectors in TPN. Sorry, TF of Pn. For V1 PK in TPM. And now we can define the pullback of A by F as the tensor field F star A on M such that F star A at P, this is just what we defined before, d F star P of A at F of P. This formula makes sense because A is a tensor field on N, so A at F of P is a tensor on TF of Pn. And now I think that this quick review is finishing. And I think we can talk about Riemannian metrics. Suppose that M is a smooth manifold as usual. Then a Riemannian metric, or simply metric, on M is a smooth, covariant, symmetric, to tensor field G. So we write tau 2m. I introduced this notation a few minutes ago, such that Gp, which is the value of this tensor field at P, P in M is an inner product on TPM. So what is a Riemannian manifold? A Riemannian manifold is a pair M G where M is a smooth manifold and G is a Riemannian metric. The manifold M can also have a boundary, and the definition would be unchanged. A word about the notation. If VW are elements of TPM, instead of using the notation GPVW for the inner product of V and W, we can also use the notation based on the brackets. The length of a vector V in TPM is denoted by this symbol, and it is equal to the square root of the inner product of V with itself. The basic example of metric is the one of the Euclidean metric on Rn. So it's it will be denoted by G bar. This is the tensor field which twitch X in Rn associates the usual dot product. So let's write this way: usual dot product on Tx Rn. This makes sense because it's possible to prove that Tx Rn can be identified with Rn. So now it's perfectly clear what does it mean dot product on Tx Rn. So if V equal Vi d dxi at x, and W is W j d dx j at x. We have that V WG bar, this is just the sum of V I W I. Okay, it's a good point where to stop. Thank you for your attention.